the day. You've made it through the conference. All right, so please welcome Sarah Sheldon. She's going to tell you about some of the cool stuff she works at IBM.
No? Oh. I don't know. This is like falling. Okay, let me know if it's all right. Okay, so I'm mostly going to focus on the work that we do at IBM in the quantum computing group, and I'll give a little bit of an overview of that work and then kind of focus on the sort of piece of it that I work on. But to just start with kind of a brief background of how I ended up in this field at IBM. I double majored in undergrad in physics and nuclear engineering because I love physics and I just thought it'd be practical to get an engineering degree as well. And nuclear engineering seemed like the most physicsy engineering I could do. So my senior year, I needed to do a senior thesis for nuclear engineering, and I went to talk to one of my professors about who should I go talk to, what would be a good topic for this senior thesis, and he asked me what had been my favorite classes so far, and I told him quantum mechanics was my favorite, which was true. I think in undergrad, quantum mechanics was the first class that really seemed like something different from high school physics. It wasn't just harder mechanics or harder E&M, but it was something really brand new math, just kind of talking about what the physics underlying everything a little bit deeper, and I thought that was awesome. So that professor that I went to talk to, it turned out he was doing some of the early research in quantum computing using NMR as a test bed for quantum computing, and he said, why don't you do your thesis with me? I ended up staying on working with him for my PhD. And I want to say a little bit about NMR quantum computing because it was sort of the earliest test bed for quantum information. And the reason for that is because the spin is sort of an easy or canonical example of a quantum system that has two states, right? So if you have some kind of molecule with nuclei that have spins, you put it in a strong magnetic field, and all of these spins will align or anti-align with the field. And we can use RF or microwave in the case of electron spins, pulses to control the state of these spins in that field. So in 1997 or so, these two groups of Ike Chuang and David Corey, who was my PhD advisor and their co-authors, they proposed using NMR to test some of the concepts from quantum information that had been coming out over kind of the previous decade. And so some of the earliest experimental results in quantum actually came from the field of NMR, including this one, which was factoring a simple factoring problem that came out in 2001 from some of my colleagues at IBM, and Matthias Steffen, who's my colleague now at IBM, was on this experiment. And going into this PhD, I had no idea that quantum computing would 10 years later be this pretty hot field with a lot of companies kind of competing against each other. I just knew that I liked quantum mechanics. So a bit of luck, but also following what you're interested in. And I think also turned out that this background in NMR ended up being really good preparation for the work that I do now at IBM. So we're a research group that encompasses kind of all aspects of quantum computing. So we have experimentalists, theorists, we have software developers, engineers. We focus on the whole system. So we're asking questions like, how do we build a quantum computer? So we fabricate devices. We also make electronics for controlling devices, and think about the whole system of how do we cool down superconducting qubit chips? How do we get inputs and outputs to them? And all of the physical stuff that has to happen. We also think about how do we program a quantum computer? So everything that happens on the device is quantum, but we have to interact with it from our classical perspective, right? So how do we program things in an efficient way? How do we compile quantum circuits down to what can actually run on our device? There's a lot of problems that are maybe trickier than you might expect. So this is the software aspect of this is actually a big part of our program now. And then finally, what applications can we run? And especially on noisy quantum computers. So there's a few kind of canonical algorithms that have been proven to have a quantum speedup, meaning that they'll work better on a quantum computer than the classical analogs. But they require kind of perfect quantum computers, universal fault-tolerant quantum computers, which I'll get to a bit more in another second. But what we have today are noisy quantum computers. So are there things that we can do that still will give an advantage on these noisy near-term quantum computers that we couldn't do classically? So what I think is really interesting about all of these questions is, I work on a piece of how do we control the qubits once they're fabricated. And I have colleagues who fabricate the device, and they're really experts in that, and colleagues who are experts in the theory, and they can provide ideas on what would be a good design for a chip, or what would be what might be the application that we're going to want to run on this thing. So because it's such a big problem, being able to work in this group, which is kind of fostered in this industry environment, my sort of niche background from NMR really fits into this overall picture. And I should mention now that we are a research group, but we also have a commercial program. And part of that is that we host devices online. So we have a number of devices, quantum devices that people can run experiments on over the cloud. So there's a number of these devices which are open to the public. So if you haven't heard of this before, you can check out our website, and you can sign up and you can run your own experiments on devices that are hosted in our lab. So there's a few 5-qubit devices, a 14-qubit device, and then for our clients who pay for special access, they have access to 20 qubits and a 53-qubit device today. Okay, so to kind of back up and start at the beginning, what is a quantum computer? So I've mentioned already that we have superconducting qubit devices. That's the specific implementation of quantum computing that we use at IBM. I'll get into that a little bit more, but I'm not going to focus so much on the hardware in this talk. Let me see a show of hands. How many people have taken quantum mechanics already? Okay, so most people. Okay, I was told we could have freshmen through 4th year, so not everyone might have had it. But how many people have talked about quantum computing in quantum mechanics class? Okay, much less. All right, so we can tell all your professors that they can have labs using our devices now. But so the gist of quantum computing is that we have this classical analog to the fundamental building block of your classical computer, which is the bit. So today in your laptop, your classical bit is a transistor that has 2 states, could be on or off, which is the building block of our binary computational language, zeros and ones. And the difference between a quantum computer and a classical computer is we have quantum bits, which are just quantum systems that have 2 states, but they obey the laws of quantum physics. So for example, it could be that spin system from NMR where it can be up or down, and that's our 0 or 1, but now that's a quantum 0 or 1. And there's a few special properties of quantum systems that you should be familiar with already that are important for quantum computing. So of course, the first thing that's different is that it can be 0, 1, or it can also be in a superposition state. So you may have seen this block sphere picture before, but I'm going to use it a lot throughout this talk. So just to be clear, I like this to represent. This is a way to represent the state of a qubit that sort of helps you visualize what's happening when you're doing operations on it. So any point on the sphere is a valid quantum state. And you can think of a vector that's starting at the origin and pointing out. The vector that's pointing towards the North Pole represents the 0 state. The vector pointing to the South Pole represents the 1 state. And then anything else on the surface of the sphere is some superposition state. So if you're pointing along the x-axis, you would be in this state, the 0 plus 1 state. And of course, these coefficients here tell you something about the probability of measuring 0 or 1. So this is a well-defined state, but you know that if you measure it, you have kind of a 50-50 chance of measuring 0 or 1. Now we can go beyond that and start combining qubits together, and then you have the second property of a quantum system that's important for quantum computers to act differently than classical computers, which is entanglement. So now we can create states like 0, 0 plus 1, 1. So they have this, our qubits have this kind of correlation that doesn't exist in classical in the classical world. So you know that if you were to measure just one qubit, the outcome of that measurement would look random. But if you measured them both, then you'd either measure 0 on both or 1 on both, right? So that's something totally non-classical. You can't flip two coins and have the outcomes always be heads or always be tails, right? So these are sort of fundamental ideas that come from quantum mechanics. And what really is important for quantum computing and how you build up quantum algorithms is the concept of interference. So when we have these superposition states, which could be of many qubits, these coefficients, while they tell you about the probabilities of measuring one outcome or another, they're actually these complex amplitudes. So by applying different operations throughout a quantum algorithm, we can change these complex amplitudes so that they kind of add and subtract in a way that some states become more probable outcomes and other states become less probable. So you have this kind of constructive or destructive interference where at the end, the most probable outcome is the solution to the problem you're trying to solve. So this is a really kind of rough, hand-wavy way of explaining how quantum algorithms work. But the concept of quantum algorithms is kind of a whole other talk, but hopefully that gives you kind of a feel for how this is different from classical computing. And importantly, there are these kind of famous quantum algorithms like Shor's factoring algorithm, Grover's search algorithm, which have been proven to have speedups over classical computing. But those require kind of the most, they require kind of the best case scenario where you have a fault-tolerant quantum computer. And what we're interested in now is what are some of the near-term applications. And quantum chemistry is sort of the first thing that people think about. And this is sort of easy to understand because we're trying to simulate actually quantum systems. So there's this famous quote from Richard Feynman who kind of spurred on the beginning of this field, that if you want to simulate nature, then you need a quantum computer because nature is quantum. So this is, I think, the reason why a lot of physicists are really into quantum computing, because of the ideas that we can study even more quantum systems by looking at things like quantum chemistry or material science. And it's really easy to see why you need a quantum computer for this. If you imagine that you have some molecule that it requires 100 orbitals to describe the state of it, then just to write out the state, you would need 2 to the 100 bits on a classical computer. Well, that's a really big number, but you could do it on a 100 qubit quantum computer. And 100 orbitals is not really that many. I think the caffeine molecule has something like 160 to describe it, and this scaling of quantum to classical blows up very quickly, right? So 300 qubits would require 2 to the 300 classical bits to describe, and that's more than the number of particles in the universe. So there's this kind of exponential scaling between quantum and classical that requires a quantum computer for some of these problems. Now, there's some other applications that people are interested in today that are kind of less obviously going to have an advantage on a quantum computer. So people are interested in quantum machine learning, quantum optimization, and there's a lot of hope that just because a quantum computer can solve a problem in a different way from a classical computer, that there will be some advantage. But it's kind of different from this case where the solution for chemistry problems is a quantum state, whereas for these, the question is, by going into the quantum world and then returning to some classical output, some classical solution at the end, is there still some advantage to solving a problem that way? So all of these applications are kind of thinking about in the near term when we have what we call noisy qubits. So maybe we have something on the tens of hundreds of qubits. Are there these applications that will be practical to run on a quantum computer? And then eventually we want to get to the place where we have fault-tolerant universal quantum computers. So this is the space where we know that there's going to be certain problems that can be solved faster on a quantum computer, but it requires many more qubits in order to build one of these. So the idea of a fault-tolerant universal computer is to take many noisy physical qubits and encode one logical qubit into many of them. And because of this encoding into many physical qubits, it blows up kind of the number of qubits that you need, or it increases the number of qubits that you need to build a logical quantum computer by quite a bit. So in the near term, we're focused on this, but we're also focused on how do we just lower the noise in a quantum computer, because in either case, you want the noise to be as low as possible. So let's talk about what that means. When we are doing a quantum algorithm, running a quantum program, our basic experiment is what we call a quantum circuit. So if you have talked about quantum computing before in your coursework, you may have seen something like this, where the idea is that you read this quantum program from left to right, where we have each line represents one qubit, and then we have a number of operations that we can perform on the different qubits. So we have single qubit gates in these green boxes. These gates here are 2 qubit gates, so those are the ones that generate entanglement. And then finally, we have measurements here. Now, if we were to run an experiment like this, which is solving this problem 7 times 10 mod 15, if we were to run it on one of our systems today, we would get a result that looks like this. So if we had a perfect system, the answer to this solution would be this bit string here, 10, and we would measure that answer every time. But because we have these noisy systems, a bunch of the time we measure here, sometimes we measure here, is clearly not perfect. So we're not gonna be doing calculations like this anytime soon. So what are the errors that are happening when we're trying to run something on a quantum computer? Well, these are some of the characteristic kind of specs for a quantum our quantum gates today. So there's a number of values that we typically measure. So T1s and T2s, these are kind of the lifetimes of our qubits. So that's how long the quantum information will stay in the state that we put it in. And this kind of sets an upper bound for how many operations can we do in a quantum circuit before it just becomes nonsense, right? And then we can characterize sort of the average noise on any one of these operations, like the single qubit gate error here, which is something on the order of 1 in 1,000. So this means that about every 1,000 times we do that gate, there's an error. We also have errors on the measurement. And then 2-qubit error rates are something closer to the 1 in 100. So as we're going towards that ultimate goal of a universal fault-tolerant quantum computer, we want to look at how close to that ideal gate are we actually performing. So there's a couple definitions just that I might be using throughout the rest of the talk, but the main thing is that we are interested in the fidelity of these gates. So how close is the operation that we're doing to the ideal operation? And that has implications for when we start to encode everything into this logical qubit, how good is our error correction actually going to be? So I've mentioned the quantum gate as the building block of that quantum circuit. And the gate is just any operation that changes the state of the qubit. So we apply some energy to the system, and it's going to move it from the ground state in hopefully a controllable way. So for superconducting qubits, the kind of qubit that we have in our lab, these controls are performed by microwave pulses. So we start in the ground state, we apply some microwave tone, and the qubit rotates by 90 degrees onto the y-axis. So this pulse would be called, or this gate would be an X90 gate. We can write it mathematically like this, and it will perform this operation where we start from a ground state and it takes us to this superposition state. Right, and we can do X, Y, Z gates, and we can do those 2-qubit gates as well. So in our systems, these are superconducting qubit systems, and they're built out of basically LC circuits. So we fabricate devices that look like this. This gray box is actually the qubit itself, and then the qubits are connected to each other by these superconducting resonators. So this, zoomed in on this box, you have basically a parallel plate capacitor, and between them a small Josephson junction. So what this means is instead of just an LC oscillator, which has a harmonic well potential, that Josephson junction is a nonlinear inductor. So it takes us from this picture to this picture where we have an anharmonic oscillator. That means that there's a resonance frequency between the 0 and 1 levels that's slightly different from the next level up. So that means we can isolate the 0 and 1 transition and control the state of the qubit by applying microwave pulses on resonance here. And at this point, I want to kind of jump back to that idea of NMR quantum computing, because the work that I do now is really, how do we control the operation here in a way that we take the qubit very carefully from one state to another state. And in NMR, a lot of these ideas have already been studied for many decades. So if we take, for an example, just an ethanol molecule, and you wanted to measure its spectrum, well, you can see that it has kind of 3 clusters of peaks here, and if you want to finally resolve it, then you're going to want to very carefully control the pulses that you're sending. So if you were to just apply some RF tone for some time and then turn it off, in Fourier space or in frequency space, that tone would look like this, the sinc function. So the spins of each of these is basically a little magnet with some resonance frequency that depends exactly on its position in this molecule. And so this spectrum here, the x-axis is the frequency of the spin. And if you're applying this sinc function in Fourier space, you might be exciting a bunch of things at once, and you would get a spectrum that's really kind of smeared out. So you wouldn't be able to identify maybe this cluster from this one or the peaks within it. So within the field of quantum control, and especially with NMR, we've done a lot of work studying shaping pulses in order to excite a more narrow range of frequencies, essentially. So if you take a Gaussian pulse and you take the Fourier transform, the Fourier of a Gaussian is a Gaussian, and you can make this a very narrow band peak in frequency space. So you can get much finer resolution in an NMR spectrum. So we actually do the exact same thing for superconducting qubits, where we just have microwave pulses instead of radio frequency pulses. And we generate this Gaussian envelope around our microwave tone. And a lot of the work we do in trying to calibrate up gates that have low noise is to find the exact shape of this Gaussian pulse. So we borrow another technique from NMR, which is called error amplification, where if we wanted to know what is the exact amplitude of this pulse in order to take us from a 0 state to a 0 + 1 state, we might apply the pulse one time. And if that amplitude is a little bit off, we might rotate over to here, so not quite onto the equator. And when we measure the state of the qubit, we would see its projection onto this z-axis. But now if we repeat that pulse a bunch of times, say we repeat it 3 times, then we go to the equator, to the South Pole, back around the other side, except we've multiplied that error by 3. So we kind of amplify the error as we keep repeating it. And if we look at the projection onto the z-axis, it's going to look something like this, where it's kind of ping-ponging around the equator, or around 1/2 here. And this is just some calibration points for 0 and 1. So I'm kind of, and then this we can fit analytically to this expression here, and then we can update the amplitude of the pulse. So there's some kind of finer tuning that we can do in terms of pulse shaping. We add another tone out of phase to get rid of some phase errors. But all of these ideas are, like I said, kind of coming from NMR and extensions to the superconducting qubits world, where we have some additional errors that we want to account for. So I've talked about that we have noisy qubits, and that we want to carefully calibrate the controls of them. But when I say noise, what noise are we really worrying about? So there's many sources of errors. One is these calibrations could be bad. So if you over or under rotate, or you're rotating around the wrong axis. You can also have that just T1 and T2, the lifetime of the qubit is finite. So in this block sphere picture, that looks like the qubit going from 1 back down to 0, or from wherever its position is down to 0. Or similarly, it's losing information in the X and Y components. We might also have errors where we didn't actually prepare the qubit in the ground state every time. So in our systems, we put our device in a dilution refrigerator, and it gets very cold, and we assume it's in the ground state. But maybe some percentage of the time it's actually not. So if you start in the wrong state, then your whole algorithm will be wrong. And then finally, there's errors that take us kind of outside this block sphere picture, like leakage, where we might drive up to these higher levels, and then we lose information from the computational space. And then additionally, there's crosstalk, where we want to apply pulses to one qubit, but it's actually coupled to another qubit. And there could be microwave leakage or something that causes something to happen on the qubit that we didn't really intend. So the sort of corollary to gate calibration is gate characterization. And for a lot of the reasons that make quantum computing interesting for solving problems, mean that it's hard to characterize these systems, right? So quantum computers are interesting for chemistry because you want to try to map some quantum system onto a finite number of quantum bits instead of some exponentially large number of classical bits. Well, if we want to characterize qubits with classical inputs and outputs, it also becomes a challenge. So one of the things that we want to do all the time is think, I calibrated this gate. Now, is it actually doing what I thought it was going to do? So you can do things like those error amplification sequences to look at one aspect of the gate. But if I want like the full map of that gate, one of the tools that we have is called quantum process tomography. And this is an experiment that gives us kind of all the information about the gate, the full quantum map. And the way that this works is we start with the qubit in the ground state, and then we rotate it along the different axes, X, Y, or Z. And then we apply the gate that we're interested in. So maybe this is, a rotation around X plus Z. And then we measure again, we do another rotation around X, Y, or Z, and then measure the final state of the qubit. So the idea is that we prepare all possible initial states and measure all possible output states, and then kind of correlate the inputs to outputs to find a map that looks like this. Now the problem with this is if we wanted to do this on more than a single qubit, it scales very poorly. So we have to do all these inputs and output measurements, which means that if you had an n-qubit tomography experiment you wanted to do, it would scale as 2 to the 2n. So if you wanted to characterize a gate on 3 or 4 qubits, maybe it's possible, but it's going to be really hard, and beyond that, you're probably just not going to do it. So a lot of the work that we do, or that I've been involved in, is trying to think of different ways to do this in a more scalable fashion. The other problem with this setup is that you are still applying gates here. So this UI and UJ are quantum operations that could also be faulty. So if you have errors in your state preparation and your measurement, then the reconstructed process that you build here is also not going to be perfect. One way around that is something that we call randomized benchmarking. And this, I'm not going to get too much into the ideas that we just apply random sequences and then undo that sequence so that the whole thing should just do an identity. And this allows us to kind of look at the decay of a qubit as a function of how long of a sequence we applied, and that gives us sort of an average value for the noise in the system. So my specialty has really been in this idea of characterization and calibration, and there's more that we can get into in terms of what do we do when we bring qubits together and we want to look at large entangled states, or if we want to look at processes on mini qubits. And that's when we start doing things like looking at random circuits. So if anyone has a particular interest in these things, I'd be happy to talk more about those later on. And I want to kind of wrap up with some commentary about just the field of quantum computing in general, because I find that it's a very interdisciplinary field, and there's a lot of ways to kind of get into it. So I come from this background of quantum control, but what I really have been attracted to in this field is that we're doing fundamental research where we get to study quantum mechanics, but there's also these very practical applications at the same time. So I come from a physics background, but we also work a lot with chemists. Now we have a commercial program, so it's interesting to study a chemistry problem or to look at how entanglement spreads on a quantum system. But then there's also things like the pharmaceutical industry is interested in learning how can you design better drugs or look at drug delivery through quantum simulation, or you might be interested in how do you how could you build a better battery for an electric car or something like that. And then of course there's a lot of computer science involved, both in terms of thinking about applications like are there quantum applications in machine learning, but also in the quantum theory, quantum information theory perspective, where a lot of this has come from originally. And finally, a lot of my colleagues come from a math background, and I didn't have I didn't have an obvious picture to put here, but there was this big result that came out last week in complexity theory, which I do not understand at all. But I just wanted to mention that because there's this field of many ideas and this problem that involves all these different components, there's kind of something new to learn every day, which I think is really, really fun. And as I mentioned, we have these devices online. If you want to explore for yourself, you can do that. And not only are the devices online, but we provide open source software called Kiska, which is on GitHub, and it's all Python based. So if you're interested in looking at that, you can. It's a really good place to kind of jump in and start exploring. And even some of the calibrations that I was talking about today, you can do for yourself through this open pulse framework, which allows you to even design kind of lower than the gate level and run experiments like the ones that I do. Finally, it's just a picture of our building in New York. I want to say that if anyone has any questions about just working in industry or in the field of quantum computing, either one, I'm happy to answer questions about that. I think it's a really unique environment where we get to address all these different aspects of a problem that I on my own would not have had the expertise to do. So I think it's a really fun way to contribute something at the same time having kind of this access to all this expertise of the people around you. So with that, I'll stop and say thank you.
All right, thank you, Sarah. Does anyone have any questions for Sarah?
Hi. You said you use superconducting qubits in the research you're doing, and I'm just wondering if they're like traditional superconductors or high temperature, and if they are high temperature, does that like introduce any new like noise or errors into the system, or is it kind of separate from those?
Right, so
errors?
we use pretty traditional superconducting materials. So we use things like niobium and aluminum. So they're actually not high temperature superconductors. So I mentioned that we have to cool down these devices in a dilution refrigerator, and that's kind of for a couple, one, so that these metals go superconducting, but then we also have to bring the qubit to the ground state, which happens at a much lower temperature. And it's not just that the material has to be superconducting, but you have to kind of remove all that thermal noise that the qubit sees. So there may be advantages to looking at different materials, but I think there's still the question of noise in the environment. So.
Hi, thank you. My question is, how far do you see the future of superconducting qubits for quantum computing as opposed to other ideas?
That's a good question. So there's a number of implementations for quantum computing that are kind of at different stages of development. I think we obviously like superconducting qubits at IBM because it kind of makes use of the long history that we have in silicon technologies and just traditional fabrication processes. But I think it's anyone's guess like what's going to be, what is the ultimate quantum computer going to look like? It's probably going to look different from what we have today. I think superconducting qubits are nice just in terms of how we can have control over how they're engineered and how they're coupled together. Coming from an NMR background where you're just given a molecule from nature, it's much more convenient to be able to tweak things and design it how you want. But there's a lot of cool stuff coming from spin qubits and from trapped ions that, trapped ions have really good low error gates that look really promising. And if you can scale up that system, that could be really cool too.
Hi, I was just going to ask what advice would you give to anyone who might be interested in quantum computing but doesn't really have an idea of where to start?
Sure. So I think today's there's a number of things. You can, not only us, but there's several kind of software frameworks that you can play around with. I think ours is really good for someone coming from a physics background because it's all Python based and kind of written in a way that's written initially by a lot of physicists. So I think it's a good way to get started. And I think you're seeing more also just kind of opportunities for getting involved in the community, like hackathons, internships, all of those things. IBM definitely does all of those. So if you want to know about specific events, I'm happy to talk to people. We've started doing what's called Kiska camps, kind of once every few months that are different places around the world, and basically like an intense hackathon. That's really fun. But I think because there are systems online today, and because there's so much open source software, it's actually pretty easy to get started. So in terms of software, you can even contribute in terms of just writing tutorials or looking at how how can you optimize circuits more efficiently. There's a lot of like easy Git issues that people can look at and jump off from.
Hi, could you tell us a little more about the different types of qubits that different labs are like exploring, and like what are the advantages and disadvantages of different ones?
Well, obviously, superconducting qubits are the best ones. There's superconducting qubits are one of the most popular ones. A lot of other companies are looking at them as well. There's trapped ions, which are a bit different because they're trapping individual ions in an E&M field, and you're kind of using this very pure system, which can give really good gates. But then if you think of how the challenges, I think there are how to scale them up, because you can't fit so many ions in some of these traps, but there's ideas there. I mean, the challenges for all of them are scaling, probably. For superconducting qubits, it's always going to be pushing the noise down and getting to longer coherence times. I think today we can kind of get in the hundreds of microseconds, which is way beyond what people thought, 10 years ago or so. The progress in that respect has gone really far. But superconducting qubits don't have as long of lifetimes as, say, trapped ions or some spin systems. But I think, let's see what else. You may have heard about topological qubits. So these are qubits that are kind of theorized or would be built on the theorized existence of a Majorana fermion that have the idea is that they would be sort of intrinsically protected from noise. The problem is that no one's actually been able to detect one for sure. So there's a lot of kind of theory built up around if that's able to be experimentally realized. There's also other stuff with optics and spins as well. They all kind of have their pros and cons.
Hi. Yeah, so I was wondering, so you were talking about like noise being a problem of quantum computing, and I was wondering if other than just technical disadvantages or something, or restrictions, what about like accessibility or economical or ethical disadvantages or restrictions?
I mean, I don't know in terms of that if there's much distinction between the different implementations. I mean, in terms of noise, a lot of what we study is, materials So are there materials properties that would give better qubits? Are there environmental things that you can make better by having cleaner signals in the fridge or better thermalization or something like that? Economical, I mean, everything, a lot of the, there's some fixed cost of just setting up the system, whether it's a vacuum system for ions or a Dilfridge system for superconducting qubits. And then a lot of the stuff around it kind of adds up as well. Like, maybe I have like a sort of snapshot of the lab here. You can't really see it, but like there's this fridge and we have all these inputs and outputs at the top, a bunch of microwave cables that go to, racks of microwave electronics. And one of the big challenges there is how do you scale all of that as well, because you don't want the room temperature electronics to just, start taking up the whole room. And that a lot of the expense comes from some of the peripheral stuff like that. So, FPGA hardware as well as kind of cryogenic microwave components and stuff like that. So that's maybe not I don't have a direct comparison between different hardware implementations, but those are some of the factors that go into it.
Hi again. I was wondering if you could talk a little bit about the pace of research in industry versus academia.
Yeah, so I would say a couple of things. It can vary. So first of all, I think my experience is probably pretty specific to working in the quantum computing group at IBM, which IBM has had a research division for forever, and it's been a really critically important part of the company. So it's always been pretty valued. And the quantum computing group has been around for decades, really. The experimental quantum computing group has been around for at least 10 years, maybe 15 years. So there has been, at least for us, this very long-term horizon for quantum computing. So there is some funding of kind of more fundamental research, or at least fundamental within the framework of computation, right? But of course, there is also, we do also now have a commercial program. Quantum computing in particular is a pretty competitive field, so that means that we have, long-term horizons for some things, and then we also have, shorter-term deadlines for other things. So having a commercial program means that we have devices online. That means that there are maintenance things that go with that. That means that we need to have kind of a schedule for when things will be released, and that's a sort of different way of operating than you maybe do just for research. You always have milestones for research, but the timelines can be different, or just what the finished product looks like could be different. So it's sort of the difference between just research and sort of research and development, if that makes sense.
This is our last question.
Hi. Just to piggyback off of what she asked, do you have any idea what the internship opportunities are like at IBM?
So we do have, we have an internship program. IBM Research in general has an internship program, and the quantum group in particular has internships. And I think I should have put websites up, but I think if you go to that quantum computing website, you can find, this one. Yeah, you can find some links to jobs as well as to internships. If anyone's really interested, you can also you can find me and I can give you some email contacts as well.
All right, and on that note, it is lunchtime. Please give another round of applause for Sarah.